Okay. Now we'll discuss Otsu's binarization technique, which is a way to determine the threshold T for binarization automatically. So what Otsu binarization does is determine threshold T given the grayscale image automatically. So before we start Otsu binarization, we have to cover a few fundamentals of probability. So some basic probability. Basics. So we know if X is a random variable and it can take a set of values, script X, then P of X is its corresponding probability distribution. Then mean of the distribution, mu, is given by sigma X into P of X, where X belongs to. X takes a value for all the instantiations of this random variable. The variance sigma squared is given by P of X. The standard stuff. Also, we discuss Bayes theorem. What does Bayes theorem say? If A and B, two events, then the conditional probability P of A given B equal to P of A intersection B divided by of B. Which is again equal to P of A with P of B given A divided by P of B. One way to remember this is P of A intersection B, or sometimes it's also written as P of AB, is P of A to P of B given A which is equal to P of B to P of A given B. So these two can be conditional probability of P of B given A. We want to find P of A given B, and we can use the conditional probability in P of A and P of B to determine P of A. This basic interface. Okay. Also, we'll discuss how do we connect histograms and probability. So what the idea here is normalized histogram can be treated as a probability mass function. So what is a probability mass function? Normally, there's a probability density function and a mass function. What's the difference? The subtle, there are systematic ways of defining it, but for this, the scope of this course, we can just look at them as PMF is for discrete cases and PDF is for continuous cases. So yeah, we are using the normalized histogram. So P of K is histogram which we have H of K divided by the number of pixels, total number of pixels. So it basically gives a probability that a pixel takes value. This is the probability, if right. Okay, now let's move to Otsu binarization. This is a fundamentals, okay? Probability and base theory. So in binarization, we have pixel values. What we're trying to achieve is there are pixel values from 0, 1, etc. up to k minus 1. We have to upload, yeah, we're assuming this is an incremental set of values. So discrete set of values which are increasing. So what we want to do is after binarization, we want 0, 1, etc. till t to be in a class 0, which is the 0 pixels, and t plus 1, etc. k minus 1 be in class 1. Let's call this class 0 or C0. Let's call this class 1 C1. This is what we are trying to achieve, right? Okay. Now let's define something known as class probabilities. So in Otsu binarization, we're actually using a probabilistic picture of finding t automatically. So what is probability that a pixel belongs to class 0? P of C0 is a probability that a pixel belongs to C0 from a k is equal to 0 to t p of k. So we have a normalized histogram, which is basically p of k, and we have the k values here. If we know this, what is the probability that it belongs to a particular class C0? Here we have a C0 and we have a C1. Yes, you just add up the probabilities of all the cases where it belongs to class C0. So we call this as omega 0. Similarly, probability of one, probability that a pixel belongs to class C1. So here we have to sum all entries from t plus 1 to k minus 1. We call this omega 1. So here we've defined both class probabilities for class 0 and class 1. So the total probability is 1 because either it has to belong to class 0 or class 1. Omega 1 is also equal to 1 minus omega. Okay. Define class probabilities. Now we have to define class math. Yeah, there's something which we have to consider. So you can ask a basic question. So the fundamental equation of the basic equation of finding the mean is the basic way of finding the mean is you're given the probability mass function, you add it up all together, right? And you get mu multiplied with the corresponding k value, x into p of x. This is the equation. But the probability function which we are taking here is not just p of c1, it's a conditional probability. So here, let's first define what is the mu which we're trying to find, mu 0. And we want to find the mean value for pixel given the pixel belongs to C0. This is how we're defining mu0, mean value of the pixel given the pixel belongs to C0. So that is basically given by mu0 is equal to sigma k is equal to 0 to k minus 1. It's actually k minus 1, but we are taking only till t because we'll see it fine. Because, okay, we'll look at it. Why? It's not required. Or let me be more specific here. Let's take all the cases till k minus 1. Okay. P of k given C0. So this P of k given C0 is probability that a pixel takes value k given it belongs to class C0. So this is the probability that pixel takes value k given belongs to C0. So how do you find this probability? So by Bayes' theorem, we have P of k given C0 into P of C0 is equal to P of C0 given k to P of k. We already know what P of k is, right? So from here, this is what we're trying to find. So P of k given C0 is equal to P of C0 given k into P of k divided by P of C0. Right? Yes. So P of k, we know we have the normalized probability distribution. P of C0, we know it is omega naught, right? But what is P of C0 given k? What does that mean? This means probability that a pixel belongs to k belongs to C0 given it has value k. Okay. Suppose we're using if k actually belongs to the first set of class values 1, 0, 1, etc. till t. In those cases, we can say P of C0 in given these case, right? These are the given case. P0 given k is equal to 1 because it's a sure event. Given these values, we're already making those values to be equal to. I mean, those values to be part of class C0. So for these set of values, this is actually equal to 1. And for k belonging to values which are t plus 1 till k minus 1, P of C0 given k actually equal to 0 because this, so of course it's falling into the other class, so it's not a probable event, right? So in mu0, even though we take probabilities from the how we have written sigma k is equal to 0 to k minus 1, this is the index which we have written for mu0 here. But one thing to notice here is that after t, right, this is actually this index is from t So k is equal to 0. Zero, etc. T plus 1, etc. K minus 1. But after t plus 1, the probability is going to be 0. Already seen here. So it's only required to index it from 0 to t, because after t, this corresponding conditional probability P of C0 given K is going to be 0. So mu 0 is 0 to K equal to 0 to T, K into P of Pk given C0. Why? Sorry. Pk, right? P of K given C0 divided by P of C0. P of C0, we all know it's omega naught. P of K given C0, for all these set of K values, it's 1. So it is basically K equal to 0 to T, K times P of K divided by omega naught. Similarly, mu1 can be written as sigma K is equal to T plus 1 to K minus 1, K into P of K divided by omega 1. So what does this mu give? This basically gives the mean value of pixel given it belongs to 0. You also have to find the overall mean. Overall mean mu t. This is for the entire image. So here a conditional probability doesn't matter. We just have to take the overall mean for the entire probability distribution. So it's sigma k 0 to k minus 1, capital K minus 1, k into P of k. So this can be again split into k is equal to 0 to k minus 1. Sorry, t k into P of k plus 0. Sigma k equal to t plus 1 to k minus 1, k into P of k. But we already seen this quantity is mu1 times omega 1. So this is mu1, mu naught omega naught plus mu1 omega 1. So this is one relation which we have. What does that mean? Yeah, mu t, the total mean value of the distribution, right, is the conditional means to the class probabilities in their product, mu 0 mu1 plus mu1 mu2. So mu1 of mu2. Okay, we've found what the class means are. Now let's look at the class variances. Class variance also we are finding in a similar fashion. We're looking at the conditional probability. So sigma naught squared is sigma, but this is actually the sum over values k equal to 0 to t, k minus mu1 squared p of k given c naught, which indeed is sigma k equal to 0 to t. We've already seen what k given c naught is. It is p of k divided by omega naught. Similarly, omega 1 squared is sigma k is equal to t plus 1 to k minus 1, k minus mu squared P of k divided by omega 1. Total image variance. T squared is k is equal to 0 to k minus 1, k minus mu t whole squared, P of k right, this is the total variance. Okay, we have these terms. We've already defined these terms. We have omega naught, we have, okay, let's quickly recap. We have the class probabilities, which is probability of C0, which is probability that a pixel belongs to a class C0, which is given by omega naught. Probability that a pixel belongs to class C1, which is given by omega 1. We have the means, these are conditional means. Probability that mean value for pixel, given that pixel belongs to C0, it's given by mu naught. And mu1 is the probability, corresponding probability that a pixel takes value k given it's belonging to class C1. In similar fashion, we have defined, we've also defined the overall mean, class variances, class conditional variances to be precise, and total image variance is also defined. Now we are defining another parameter called within class variance. Define intra-class intra-class variance. And the താഴത്തിന്റെ പേഴ്സൺ ആക്കുന്നു. So we define something known as intra-class variance. So what intra-class variance is, suppose we have two classes, right? Let's say this is the mean of this class and this is the mean of this class. And these are the variances, right? This is class 0 and this is class 1. So you're just using a threshold T. Inter-class variance is within class variance is how the data is, how much variance we have within a particular class. So one you're looking at is this one has this interclass variance, while this has a large interclass variance. For intra-class variance. Within a particular class, there is a lot of variance. Okay. So which is the ideal case? Ideally, we want very less variance within a particular class and very lot of variance within two different classes. So within class variance should be minimum. So how do you define interclass variance? Is something which is not worthy. So note that this variance is not the total variance. Within class variance is defined as omega naught sigma naught squared plus omega 1 sigma 1 squared. This is how we define interclass variance. Why is it defined so? Is another question. Why are we defining? Okay. So it happens that omega naught, sigma 1, and omega 1, all these are functions of t. Because the summation depends on t here, right? T and t plus 1. So this is actually a function of t. Omega naught is a function of t. So what is our goal? Our goal is to minimize the intra-class variance. Intra-class variance. So the goal of thresholding. Just to minimize. Sigma omega square. So find a T star such that argument 0 less than equal to T less than equal to K minus 1. Sigma squared so we have to solve this optimization problem to find the optimal T star, which minimizes the interclass variance. But it happens that solving this problem is a bit more involved. It's complex to optimize this, and it requires second-order statistics. So we define something known as between class variance. Define between class variance or interclass variance. Sigma b squared is equal to omega naught naught into. So how have we defined interclass variance or within class variance? This is omega naught into sigma naught squared plus omega 1 to sigma 1 squared. Here we're defining it as omega naught into mu minus mu t whole squared plus omega 1 mu 1 minus mu t whole squared. So not exactly sigma, right? Very different. This is how we're defining between class variance. It happens we have a relation between class variance and within class variance. Between class variance squared plus within class variance squared is actually equal to the total variance, which is something which is independent of t. This is a constant for a given image. So if we are trying to minimize this, then if we can maximize sigma b squared, it basically gives the same result. So between class variance is much more easier to optimize. How do we get this relation? We can actually try and prove this is actually true, which we can work it out. So instead of solving between class variance, we can actually solve. So within class variance, we can, instead of trying to minimize within class variance, we can actually solve the optimization problem. T stat is arg max 0 less than equal to t less than equal to k minus 1 sigma b square of t. This is an easier problem solve. Right. I currently is not within the scope of this lecture. So this is what we have for binarization.